Yeah, welcome to our little conceptbase channel. In the last episode, we learned how to represent example and relationship models and their instances. You see here the graphical representation with the meta classes here, defining the entity relationship modeling notation, an example ER diagram, and some example data. Now, the next task is to define another modeling notation for a process model. Before we start, though, I would like to point that there are some predefined objects in conceptbase that we need to know before we continue. So let's right-click on entity type and see what are the classes of entity type. So it has no explicit classes, but it has so-called derived classes, in this case two. Individual means all objects that are displayed like a node, and proposition means any object, so including links like this one here that is called a link or an attribute. The most important one is proposition. So the proposition, let's show that in the Taylor's editor, has a whole bunch of properties. So this is the attribute property, and for example, the row link of relationship type has been instantiated from this attribute. We can even show it here. So you can right-click on the row link and see what it is instance of, and it's instance of the attribute of proposition. So you see it here. Now these links are dotted here, and means this is not explicit information, it's derived. So there's a rule inside conceptbase, a predefined rule that says every thing that is in the database is an instance of proposition. Yeah, this row link also is an instance of proposition as well, you see here. And all that looks like a link here, that is an instance of attribute. Yeah, so we can use this for defining some very high-level properties of any objects. And that's what we're going to do first. The high-level property that we like to that I like to define here is the transitivity of links. So, for example, if you have an ancestor A and this person has an ancestor B, then B is also your own ancestor. So the parent of your parent is your grandparent, and so forth. That is a transitive relation. Many relations are transitive. In process modeling, the successor relation between tasks, that shall be defined to be transitive. And I would like to have a definition of transitivity that is reusable for many cases. So we do that by defining transitivity as a new property of proposition. So we add a new attribute transitive to proposition, and here we define a rule. So let's read it. The last line is the most important one. So if X, which is any object, is related to Y by a relation R, and Y is related to another object Z by the same relation, then X is also related to Z. That's the transitivity. And that's highly reusable. So the expression here, that is a so-called predicate, that's about the relation R as such, whether it is explicit or derived, it doesn't matter. This here, A underscore E, is the same relation R, but here we only consider explicit connection. So X and Y are directly connected. So in other words, if X and Y is directly connected and Y is directly or indirectly connected to Z, then X is also indirectly connected to Z. So this is so-called rule, a deductive rule that derives new solutions to the predicate X are Y. And let's tell that, and that's successful. So now we have this general property defined for proposition, and we can define our very simple process modeling notation that just has tasks and agents. So a task is related to another task by a successor relation, and we define this relation to be transitive. Yeah, so then we can talk about that task 1 is related transitively to task 2, independently whether there are many tasks in between. So the rule will take care of that. And we have another object or class agent that is linked to task. An agent executes a task. So let's tell that. And we have that. Now let's define some analysis queries for the process modeling notation. So a start task is a task that has no predecessor. So a start statement is a task. So it is a subset of all tasks. The ISR means specialization or subset. It's a query class, and that means it will take all the instances of task as possible candidates, and those that fulfill the membership constraint, they are instances of start statement. Yeah, and the membership constraint said constraint says that there is no task T such that T has this task that stands for any instance of task as successor. So if there is no predecessor T, then it's a start statement. That's the first one. The second one is slightly more complicated. That's a so-called predicate task. A predicate task has two successors, two explicit successors. So there are two successors as 1 as 2, such that this has successor as 1 and this has successor as 2, and the two are different from each other. So it's important to have this condition because this is a logical variable, and if you have some task that has a successor, then this successor can be a filler for S1 and at the same time a filler for S2. So we have to explicitly constrain that by this predicate S is not equal to S2. So let's tell that. That's the second one. Now the third query is a bit more, is even more complicated. That is a loop task. A loop task is any task that is in some loop, and that means you take any task of that loop, then you can go from that loop statement to this representative and then back to the original task. So we have to pick some representative. That's a parameter of the query, rep, representative. And if a task is a member of this of a loop denoted by this representative, if you can go from this task of the loop to the representative, and then from the representative back to the same task, this. and there must be at least one successor of this representative, and you must be able to go back from this successor back to the representative. So this is a non-trivial loop. So that's this one. And now with this definition, you can just define loop task as such to be a subclass of loop task of. So then you don't need a representative. It will take any representative to find out whether something is a loop task. Yeah, so this is not a very easy definition of a loop, but anyway, you can look it up in the tutorial that I link below this video. So now let's link the analysis of agents to that. So the next task would be, the next challenge would be to define which agents have so-called split responsibility. So they are responsible for one task T1, and then there is some other task T in between. And then from T, you can go to another task T2 that is executed by the same original agent. So this agent executes T1 and also T2, and there is a task T in between. And the task T is executed by another agent A that is different from the agent that we are interested in. Okay, so that is this challenge. So let's add that to our capabilities of the process model. The more queries we have like that, the more we can analyze our process model. So now let's define some example process model of our insurance application. Yeah, so we have a start of the whole process that goes to receive claim. From receive claim, we go to check policy. Check policy, we have two successors. This is a so-called predicate statement. We can either assign an assessor or we can directly propose a payment. Assign assessor will then assess a damage, and afterwards we go to the proposed damage. Proposed damage has two successor, either accept or reject. This is done probably by the insurance holder. Process payment is the end. It goes to the end. So this is the end of the whole process. So the assessor is responsible for this task. Insurance agent is responsible for receive claim, propose payment, and that's it. So let's tell this process and add that to our representation. Let's remove this one here and start the graph editor with a start statement. So this is the start at an instance of tasks. Yeah, so outgoing attribute successor that goes to receive claim. From receive claim, you go to check policy. And there you have two possible choices. So assign assessor or propose statement, propose payment. Then from here you go to assess damage. there you go back to propose payment, and then you outgoing attribute process payment. Forgot one. So here we have the reject case, and from here we go to finish. Yeah, so obviously this is a loop here, and this could also go to a loop. So this is done by the probably by the customer that can reject the payment. Good. So let's add here agents as a class and see what the instances are. So we have 2 instances. Let's hide this agent object again. So we have assessor and insurance agent. This one executes these 2, and the assessor executes just this one here. Good. So we don't have a dedicated symbols for the task and the insurance agent. It all looks like rectangles. We will learn later how to assign different graphical types to the different elements of such a graph. But still we can check whether our queries work. So insurance agent is obviously an agent with split responsibility. So it's instance of agent, but also of our query agent with split responsibility, because this person is responsible for this and for that, and in between is something there where this person is not responsible for. Good. This is obviously the start. So let's see whether this is a start statement. That's another query that we defined. So that's instance of start statement. So that also works. Now we have a loop. So let's see whether this is a loop statement. That's instance of loop task. Yeah, indeed. So this is part of a loop. This is not part of a loop. Process payment. Let's see whether it's part of a loop. It's not part of a loop. You can also check these queries in a textual way. So you can, under Browse, display queries, view the queries, and let's see a loop task, and query that, and then you see all statements, all tasks that are in a loop. These are the 4 statements that are in a loop, and actually they are in the same loop. If we ask the other query, then we are asked to check the representative, and well, let's take a check policy, and it turns out that all these 4 tasks are member of the same loop. Yeah, so that is the definition of a process modeling notation and quite sophisticated analysis queries for that. So finally, I would like to link the process modeling notation with our entry relationship diagrams. So a task should be able to have some entity type or relationship type as an input, data input, or data output. To do so, we first define a superclass of entity type and relationship type called object type. So entity type is a subclass of object type, and relationship type is a subclass of object type. So we do so because both of them could be input or output of a task. So information that flows into a task or information that is created by a task. Now, defining the input and output is just two more attributes of task. So the input can be an object type and the output can also be an object type. Very simple. Now we have connected the two notations, ER models and relationship models, and the process modeling notation, a very simple process modeling notation. That is at the meta class level. We are talking about object types, relationship type, entity type, and tasks. Now let's use that for our example process model. And let's say that receive claim creates the claim. So that creates an object of the entity type claim. And check policy that uses the claim policy link to check whether the claim is valid. Yeah, so this is using the linkage between task and object types to actually link the two sides. Yeah, that completes this part. You can we can see whether yeah, the check policy actually now have that. So let's first validate and update the elements of this graph, and now see whether that has some input. Yeah, and indeed it has claim policy as an input. So we actually linked the two sides. Yeah, that's all for now, and thank you for listening. Bye.